Zemax, and I'll be discussing dynamic focusing liquid crystal lenses and how a user-defined surface can be created for OpticStudio to simulate these effects. Through the course of this webinar, I will introduce the principles of liquid crystal lenses and their dynamic focusing capabilities, derive specifications for our final system, briefly address the built-in gradient index surfaces which could be used to model a liquid crystal lens, and finally, guide you through creating a user-defined surface for this application. To address why dynamic focusing lenses are so desirable, we should consider the need for bifocals or reading glasses. People over the age of 45 typically experience what is known in ophthalmology as presbyopia, an acquired rigidity of the eye's lens which renders it unable to be adjusted by eye muscles. Those who don't suffer presbyopia are able to automatically adjust their vision for objects of differing distances, but the rigidity of older lenses means this can no longer be done within the eye itself. The customary treatment for this is eye lenses with fixed focal lengths to correct for a specific object distance. This leads to patients using reading glasses only for close-range vision or looking through specific portions of their bifocals to achieve the necessary correction, both of which are relatively clumsy methods. Liquid crystal lenses with an attached processor performing calculations and controlling the index would be capable of adjusting their optical power in real time. The potential for this system is a pair of eyeglasses which can predict where the wearer is looking and correct their vision automatically. The core principle at work is the birefringent property of liquid crystals, by which the refractive index can be controlled using an electric field. A birefringent material has an ordinary refractive index, when the molecules are in line with incident rays, and an extraordinary index, when the molecules and rays are orthogonal, and for all other circumstances the index is a function of angle. Because of the angular dependence, refractive index can be controlled with an applied electric field, as the molecules will align along the field vector. Applying a voltage or electric field which varies across the surface of the lens will then create an index gradient. With this method, a lens of any prescription can be created by applying the proper voltage profile. A dynamic focusing lens of this design derives its optical power from its gradient index profile. Unlike a standard lens in which the power comes from the curved surfaces and rays only refract at the surfaces, gradient or GRIN lenses cause incident rays to refract continuously within the medium. A dynamic focusing lens of this design derives its optical power from its gradient index profile. Unlike a standard lens in which the power comes from the curved surfaces and rays only reflect at the surfaces, gradient or GRIN lenses cause incident rays to refract continuously within the medium. Although dynamically controlled lenses of this design have been used in the past, a startup company, Deep Optics, has proposed a method for incorporating them on a scale of eyeglasses. Their design applies a transparent electrode grid to the front of the liquid crystal rather than the edges, such that there is better control over the voltage profile and its corresponding index gradient. Additionally, this method is able to actively change the center of the lens, allowing it to align with the user's pupil. The dynamic function of the lens would be achieved by measuring the wearer's eyes to predict where they want to focus, calculating the necessary focal length or index profile, and applying the field. An IR senses in the glass's frame tracks the interpupillary distance, which decreases when you focus on something close. You can test this by trying to see the tip of your nose. Are your eyes crossed? A microprocessor, also included in the frame, performs the requisite calculations and applies the voltage profile. Because this lens design is meant to work with the user's own eyes, we will need to create an eyeball. Human eyes have already been modeled in OpticStudio and can be downloaded from the knowledge base article. We will use the one for which the image surface is on the retina, such that we can observe how the design would work for the wearer. This eye model can also be used to better demonstrate presbyopia. Simulating an object at 3 representative distances without changing the eye shows how the retinal image worsens for nearer objects, much like a presbyopic eye, which is only focused for infinity and cannot change. Our specifications for system performance come both from the proposed eyeglasses of Deep Optics and from the performance of a healthy eye. Additionally, we will concern ourselves only with the case of presbyopia and focusing assistance. That is, we will not be correcting for other vision defects such as nearsightedness. As a safety feature, we want zero optical power when there is no applied voltage profile. This means that the user will remain focused at infinity in the case of a power failure during tasks such as driving. For the design, it means that the liquid crystal lens and its substrates will be composed of planar surfaces, such that the only optical power comes from the index gradient. We want to be able to focus on objects over a continuous distance from what is considered near up to infinity. Representative distances at which we will optimize and observe simulations will be 300 millimeters, 700 millimeters, and 1000 millimeters. Finally, we will take performance characteristics from the eye model with an object at infinity. Shown here are the MTF plot and spot size achieved in this situation. The RMS radius is on the order of 30 millimeters and will indicate how well focused objects are at the retina. The MTF plot indicates the degree of achievable detail resolution, and our optimized index profiles will be compared to this benchmark plot. We will use materials based on proposed liquid crystal lenses. E7 is a liquid crystal with relatively high birefringence at about 0.2 depending on wavelength, which has been used in similar designs. The electrode material must be transparent in the visible range and sufficiently conductive to control the E7. Indium tin oxide, ITO, is again a common choice in this application. These materials are not included in OpticStudio's material libraries, so we will use the Fit Index Data option to define new classes. We'll use dispersion data coming from refractiveindex.info. OpticStudio does not allow users to alter its native material catalogs. So the process of creating new materials starts with selecting a catalog and saving a copy of it under a new name. The new copied catalog can be altered, so we are free to delete the original glasses we don't need, fit new index data, and save the new material. We can delete the selected glass by using the Cut Glass button. And we can create new materials using the Fit Index Data. Here, we would type in data from refractiveindex.info, the wavelength first, and the index at that value. We need 6 data points to fit an equation, so we will input random values to model how we would fit an index data. 0.75 microns, and we'll use 1.4. Now we can select Fit Index Data, and it fits the equation and provides us with the dispersion coefficients. The resultant system with a user-defined surface will consist of 2 main groups. The first contains the glass substrates, electrodes, and liquid crystal, and will be optimized in the course of our design. The second is the eye model and should be unchanged from the available model. The catalogs for all the custom materials used in this system are available for download in the article attachments. The position data shown here is for the final system in units of millimeters. The surface parameters depend on which gradient model we use and will be optimized and discussed in more detail later. The entrance pupil diameter was set to 15 millimeters, F, D, and C wavelengths were used, and we focused on the on-axis field. OpticStudio has built-in gradient surfaces available under surface type. These contain built-in functions for defining index profiles through the volume of the lens. The most basic, gradient 1, uses a parabolic profile, and additional gradient surfaces add higher order positions or wavelength terms. The coefficients for the terms are defined in the data editor, so these surface types can be directly optimized. However, we are limited to profile equations which are already included in OpticStudio. Gradient 1 will be sufficient to demonstrate use of these surfaces, but higher order terms can produce more complex profiles, which may prove to be more applicable in modeling the physical or electrical effects of the voltage profile on the index. The equation for the gradient 1 surface has 3 terms: the nominal index, an r-squared spatial term, and an r-spatial term. 4 parameters define the surface in the lens data editor. Delta T controls the distance along the optical axis, after which the ray direction is recalculated. N0 is the nominal index, and NR1 and NR2 are the coefficients of the r and r squared terms, respectively. Shown here are the values which automatically populate the editor when the surface is first selected. Delta t should be smaller than the width of our lens, enough to allow multiple recalculations. The nominal index can start at approximately 1.75, near the extraordinary index value, which is the upper limit of our material. The coefficients should start out negative to create a converging lens and should be small enough that the index values are realistic over the whole lens. Turning to the GRIN profile option, we see peaks at 1.75 and only decreases to about 1.69 at the edge. We will want to optimize for focus and resolution. Spot size should be optimized first, as for an unfocused or poorly focused system, MTF is too low to calculate accurately. Turning to the MTF plot viewer, we see evidence of this in the sampling too low errors shown. Only two merit function operands are needed for this first step. These are a maximum and minimum index limits, which will keep the optimization algorithm from pushing the index beyond the possible values for our material. Here set as 1.77, the extraordinary index value, and 1.53, the approximate ordinary index value. A quick optimization shows relatively little changes to our data editor, but updating the MTF window shows that our sampling error is no longer present. MTF optimization uses two parameters for each frequency of interest. One parameter pulls the current value at that frequency, and the other adds to the merit function only if the value is less than the target specification. Spatial frequencies of 10, 20, and 30 line pairs per millimeter will be sufficient to optimize our gradient. After a quick representative optimization, we can see that the MTF value has increased. And for a more direct comparison, we can see the results of the unoptimized, uncorrected image simulation through the eye model on the left, compared to the post-optimization in the near range, the 300 millimeter object distance. The same image simulation is shown for the mid-range. Again, on the left is the uncorrected version through the Zemax Eye model, and on the right is the optimized version using the gradient 1 surface. We can see a marked improvement. The other built-in option is the grid gradient, which pulls data from an external file defining the index for a grid of coordinates. The index between these coordinates is calculated via tricubic spline, so this is a good model for an electrode grid for which the index is controlled at distinct points. Additionally, the grid file makes it easy to include dispersion data, as it calculates the index based on the dispersion equation and coefficients, which can be directly copied from the glass catalog files. The grid file must contain two sections. The first row is the header, which declares the dispersion equation, the number of x, y, and z values, and the x, y, and z step sizes. The body contains all following rows. The first three columns of the body are the coordinates, the x, y, and z values. The fourth column is the index offset, and the next 10 are dispersion coefficients, which should be 0 if dispersion is unused or if the equation does not require all 10 coefficients. Based on availability, I used Excel to automatically populate the index column with values as a function of the coordinates for that row. A spreadsheet program was useful because the data maintains its formatting when copied from a spreadsheet into a code editor, from which it can be saved as a GGD file with the rest of OpticStudio's material data, which are already present in your documents. For those with coding knowledge, it may be easier to define code in, say, MATLAB to automatically generate a matrix with the requisite coordinates. For this model, I used the same equation as used for the gradient 1 surface, with the coefficients pulled from the respective optimizations. The index offset was calculated to be nominally 0, and the index calculated from the dispersion equation will be added to this offset. The shot dispersion coefficients can be found in the AGF file under Zemax's material file called GlassCat, and can be copied directly to the GGD file. To access this file from ZOS, it must be saved to the Glass Catalog folder GlassCat, which is stored with the other Zemax documents. Once the grid file is saved, applying it is as simple as selecting the grid surface type in the data editor and choosing the appropriate data file. Because the index profile is hard-coded into an attached file, it cannot be optimized in OpticStudio. Although we get good results using the coefficients found from the gradient 1 optimizations shown previously, and the grid gradient provides an easy way to incorporate dispersion, as a surface type it is consequently less versatile. As in the near range of vision, the mid-range shows marked improvement over the uncorrected simulation using a grid gradient surface to focus at the object. A user-defined surface is a much more powerful option for defining gradient index lenses, but this process adds a lot of complexity. In addition to the index profile, the UDS allows for additional calculations, which is where the interpupillary distance calculation to determine where the eye should focus would come in. Additionally, this coding option would allow for actively modeling the effects of a voltage profile, or for calculating a requisite focal length in order to properly focus. User-defined surfaces are coded in a separate platform to contain all the information on the surface, from the sag and refractive index parameters of the lens to the code for tracing rays. This information, along with input data and the parameters for the lens data editor, are compiled in a separate DLL file type which can be called within OpticStudio. A dynamic link library, a DLL, is the Windows method of interfacing functions and data with other applications. This example will cover how to compile a DLL file in Visual Studio to be used with OpticStudio. Upon opening a new project in Visual Studio, the best method is to select a Win32 console application. Selecting and naming this application opens a dialog box, from which we can select the DLL option. Additionally, we will be using a header from Zemax itself, so we can uncheck the precompiled header option. Having created our Visual Studio project, we are ready to add the necessary files. Zemax provides several sample DLL and C files, which can be viewed on the hard drive in the program files under DLL and surfaces. Because much of the code will remain the same, such as ray traces and interfacing with OpticStudio, the safest method is to open a sample code and modify it to meet the needs of a new surface. Files are imported by right-clicking in the Solution Explorer on the folder under which we want to add. We will select Add and Existing Item to import one of the samples. There are many available, but US GRIN is closest to our needs as it is a gradient index surface. Selecting the C source, not the application extension, the DLL, we can add, and it will appear in our Solution Explorer, and we can open and view the code. Additionally, we will need to add a header file through the same process. While there are many DLL and C-source samples, there is only one header file, usersurf. This is because this code is common to all user-defined surfaces in OpticStudio. Having added a source file and a header file, we can build the solution. An error message appears, originating from DLL main. Importing a sample file left us with too many code sources calling the same files and functions, so deleting DLL main resolves the errors. There should now be 3 header files and 3 source files, and we should be able to build without error. 1 success, 0 failures. The header file usersurf.h initiates the conversation with OpticStudio by pulling relevant data. The header file code defines fixed data types, which are filled with the parameter values already defined for the system in Zemax, such as the wavelength or the index value. There are 4 fixed data groups. Fixed data 4 is the most up-to-date and is used by current OpticStudio editions. Additionally, it contains far more variables and options than earlier data classes. However, OpticStudio is back compatible, and we can call any of the fixed data groups which contains the variables we need. We can use this data in our DLL with the code shown. Our header file initiates the conversation with OpticStudio by pulling relevant data. The header file code defines fixed data types, which are filled with the parameter values already defined for the system in Zemax, such as wavelengths, index, and other parameters. There are 4 fixed data groups defined in the header. Fixed data 4 is the most recent and is used by current editions of OpticStudio. It has far more variables defined than earlier editions, but OpticStudio is back compatible, and we can call any fixed data group that contains the variables we need. We can use this data in our DLL with the code shown, where FD directs the program to the fixed data group, and the following phrase corresponds to the variable within the fixed data which we want to use. The DLL export function sends defined values back to OpticStudio based on numerical signals from the program indicating what information it currently needs. This command is divided into 8 cases, 0 through 7, which may be subdivided into additional cases. The case number acts as a flag from OpticStudio, mapping requests to the correct DLL data. Case 1 represents the request for parameter names to be added to the lens data editor, and the subcase numbers correspond to parameter numbers. As ours is a gradient index surface, parameter 1 is required to be the maximum step size, delta t, but the same code format can be followed to modify or add subsequent parameters in order to fully define the surface. For the US GRIN example, which we've imported, the parameters are delta t, n0, and a. Returning a null string defines that all following parameters are unused. After creating new parameter columns, we will need to set initial values to populate them. OpticStudio requests this information using case flag 7, referred to as safe data. Each parameter will be called in order to alter the fixed data. This happens once, where we define what the fixed data should contain to begin with. After this, the fixed data will remain the same, because it is what is passed to the DLL from OpticStudio. Here, the safe data is a step size of 1 millimeter, a nominal index of 1.5, and a zero value coefficient for the equation. The values we set here will be used when the surface is first selected in Zemax and can be adjusted within the data editor like any other surface. Rather than call the fixed data command every time we use a value from the header, we may want to assign fixed data values or intermediate calculation steps to an additional variable, as shown in line 158. Any variable used, however, must first be initialized in the DLL export command, as shown in line 26. After defining variables in DLL export and assigning a value to that variable under the case number, the variable can be called by typing its names. Once we have calculated a value or function within the DLL which we wish to pass to OpticStudio, we will need to actively declare it. The user-defined data group does not automatically update. For example, line 165, an equivalency statement, which assigns a value to the variable index, does not automatically update the value for index under the user-defined group. Instead, we must call user-defined, tell it we are assigning to index, and then equate this value to our calculated result. Now, index will be able to be passed to OpticStudio to be used in additional calculations using the surface. After finishing edits to the source code, a DLL file can be generated by building the solution. If there are no errors, the DLL file in the folder for this project will be updated with the changes. This file is accessed under Visual Studio, in this case 2015, Projects, and the name of our project, in this case Examples. Under Debug, the DLL file is shown as examples.dll. This file must be copied to the same program file folder which contains the sample DLLs in order to be accessed by OpticStudio. The header file we added initiates the conversation with OpticStudio by pulling relevant data. The header file code defines fixed data types which are filled with the parameter values already defined for the system in Zemax, such as the wavelength, field, and material values. There are 4 fixed data groups defined. Fixed data 4 is the most recent and contains more parameters, but the program is back compatible and our code can call on any group which contains the variables we need. We can use this data in our DLL with the code shown, where FD directs the program to the fixed data group, and the phrase following it corresponds to a variable pulled from OpticStudio as defined in the header. This is how we will allow for dispersion in our GRIN surface, as simply using the variable name N2 in our code directs OpticStudio to access the material data we have already defined for the surface. The DLL export function sends defined values back to OpticStudio based on numerical signals from the program indicating what information it currently needs. This command is divided into 8 cases, 0 through 7, which may be subdivided into additional cases. Shown are cases 1 and 7 as main subdivisions of our code, where case 1 is further divided into subcases. The case number acts as a flag mapping requests from OpticStudio to the correct data within the DLL. Case 1 requests the parameter names which will be added to the lens data editor, with the subcase numbers corresponding to parameter numbers. As ours is a gradient index surface, parameter 1 is required to be the maximum step size, delta t. But the same code format can be used to modify or add subsequent parameters in order to fully define the surface. After creating new parameter columns, we will need to set initial values to populate them. OpticStudio requests this information using case flag 7, in which it requests the safe data. And in this section, we will directly modify the fixed data pulled from OpticStudio. The header file will have already pulled the values from the lens data editor before we added the surface and applied them to the appropriate variables, in this case, a vector containing all the parameters. We use the code shown, fd followed by the parameter of interest and an equivalency statement, to access and modify this fixed data. The values we set here will be used when the surface is first selected in Zemax and can be adjusted within the data editor like any other surface. Any variable used throughout the code must be initialized in the DLL export command at the beginning of the source code. After this initialization, a variable can be assigned a value through simple equivalency statements. This value can be a value from OpticStudio or the output of a calculation which will be in turn passed to OpticStudio. Once we have calculated a value or function to be used in OpticStudio, we must actively export it to the program. The user-defined data group does not automatically update, so we first call the variable we wish to update, in this case UD, followed by index, and then equate it to our calculation result, again using index, which was calculated a few lines above. After finishing edits to the source code, a DLL file can be generated by building the solution. If there are no errors, the DLL file in the folder for this project will be updated with the changes. This file must then be copied to Zemax's program files, from which we obtained the header and sample code file, in order for it to be accessed by OpticStudio. There are 3 parameter types to define our gradient index surface. Delta t is standard to all GRIN surfaces and controls how often the rays are recalculated within the sample. The index offset adds or subtracts from the index value defined by the material, a helpful option for keeping the profile within the material's range of values. Finally, the lens data editor will include as many coefficient values as needed for the number of terms in the equation. The equation in this example closely follows the gradient 1 profile with an r and r squared term, but the DLL can define any profile which can be mathematically solved. The nominal index value here is set by the material of the surface, Ne7, rather than a parameter, and it is this change which allows the surface to demonstrate the dispersion of the liquid crystal as well. We counter this decrease in control over the equation with an index offset parameter. This is especially useful for more complex profiles in which the nominal or zero value may not be the maximum. Using the offset will prevent the profile from extending above the material value. NR2 and NR1, as before, are the coefficients of the spatial terms. Although we only used 2 terms here, a higher order equation could be used. To use the surface we created in OpticStudio, we should select a surface type of user-defined, and then access the Properties drop-down menu. We can select a DLL file for this surface from this drop-down. If the DLL file we created is not present, be sure that it was correctly added to the program files. We can observe the parameters we defined for this surface as well. We have a delta t, an index offset, and 2 coefficients for the profile equation. We will optimize our system in the same way we optimized the gradient 1 surface, first with the spot size and then with the MTF. However, this time, because our DLL code contains dispersion information, we will need to add commands to our merit function. We defined 3 wavelengths for our system, F, D, and C. So for each wavelength, we will need to define a maximum and a minimum index value, which in this case should correspond to the material's value at that wavelength. Running the optimization as before will give the results shown. Here we can see a clear improvement in the near range, the 300 millimeter range, over the uncorrected eye model. And again, we see improvement over the uncorrected model in the mid-range. However, you may notice that the images are not perfect. If we go on to compare them to our eye model at infinity without corrective lenses, we see that the images are of similar detail and quality. Moreover, we can see that our MTF plots, once optimized, are well within the limits set by our eye model. Questions can be submitted to the webinar control panel. Thank you for your interest in this topic.